Assalamualaikum and good night. So this is finally the final topic for this protection system and introduction. Short circuit calculation. Alright, so this is additional notes. So this might be useful for even university students who are just starting to learn Power System 1 in terms of per unit method for balanced fault only. Unbalanced fault, this is not the method. For unbalanced fault, you have to use the conventional positive sequence, negative sequence and zero sequence impedance single line diagram. Okay, so we'll start with short circuit calculation, our final topic under the protection system and introduction series. Alright, so under this short circuit calculation, I will share with you, let's go through again our third year or fourth year university years, the per unit method, MVA method, which they never taught you in university. If they had taught you in university for MVA method, I'm sure you will score for the balance fault calculation. And finally, some sample exercise. Okay, so for this short circuit calculation, I will provide you this presentation material specifically for this short circuit calculation. So per unit method, we go through the conventional one first. Okay, so this is the per unit introduction. So you have your apparent power per unit, which is all the apparent power of your equipment divided by the selected base apparent power. Then voltage per unit is the voltage of your equipment divided by the base voltage of your selection. Then your same goes for your current. Is equals to the current divided by the base current, and Z per unit equals to the impedance divided by the base impedance. So for per unit introduction, you only need to specify these two value first. For example, okay, let us set the voltage for this bus at 11 kV, while the base is 100 MVA. So 100 MVA will be the base apparent power for all the voltage level. What else for the 11 kV? You have to set for every if there's a lot of transformation from 132 to 11, so it's easiest to select the base voltage the same as your transformer voltage primary and secondary rating. Okay, then from these two values you can calculate your I base and also your Z base. So like in this case, I base is just your apparent base divided by the square root 3 times the base voltage, where else your Z base is the V base divided by square root 3 divided by the I base. Or in another manner, you can also write that as Z base equals to the V base squared divided by the S base squared, the square of the voltage base divided by the apparent power base. Okay, so this, you don't really have to memorize all this because I don't think you'll be doing the hand calculation that much, but it will help you to check quickly on whether your consultant has done a tremendous or very poor job in terms of doing the programming for your power system study, like using the ETAP or SKM or power system. Okay, so this is Z new per unit. So this one will be used for the transformer lah. So the Z new per unit will be equals to the Z old per unit times the new base divided by the old base. So this new base is your selected base here. If 100 MVA is 100 MVA lah. We will go through one by one lah, by equipment. And if there's a change in terms of voltage, then you will also include here lah. Will also be the old voltage divided by the new voltage or the base voltage. Okay, if the voltage bases are the same, so it just becomes like this lah. Z new per unit equals to Z old per unit divided times S new base divided by the S old base. Okay, for example, like a transformer is a 10 MVA with Z equals to 10%. So the old base is 10 MVA. While else the selected base that you have put initially is 100 MVA. So 100 MVA divided by 10 lah. So the Z old base is 10% lah, which is 0.1 lah. Okay, then that will equate to the new Z per unit. Alright. So steps for per unit, you have to identify the S base and the V bases, then calculate I base and Z base from this value for each voltage level. So each voltage level you will have a different I base and Z base and also V base. Convert all equipment impedances to per unit, then reduce all the per unit impedances to the point of fault and calculate the final impedance. Means you have to reduce all the impedances to the point of fault. So we'll go through after this. Fault current at a particular point is the short circuit equals to V per unit divided by the Z short circuit. So normally V per unit is 1.0 lah. But if you're using IEC 60909, you may be using 1.05 or 1.1 lah. Okay, so the actual fault current will be the calculated I short circuit per unit times the I base. So repeat step 4 to 6 to find the fault current at other points. Okay, so let us see here. So we don't have a single line here. So how would the single line look like? Oh, this one is just an example lah. So set base MVA voltage. These are the two parameters that you need to set. Then calculate I and R or the Z lah for the each voltage level lah. So choose S base. You can choose any two parameters. For example, this case, S base we select as 100 MVA and V132 kV bus. V132 kV bus is equals to 132 kV. Let's say that there's a lot of voltage transformation going from 132 kV to 33 kV, 11 kV and 0.4 kV. And we select the voltage base for each voltage level the same as the voltage level lah. For example, if it's 33 kV, we select voltage base as 33. 11 kV, also 11 kV. So we know that MVA base is constant throughout the voltage level. So 100 MVA. So we already have these two parameters for each voltage level. For example, at 132 kV, let's calculate the I base and Z base. So I base is just S base divided by the voltage divided by times square root 3. So you get some value. Whereas the Z base equals to the voltage at 132 squared divided by the S base. Okay, so in this case, it's just 132 kV for I base. It's just 100 MVA divided by square root 3 times 132, and you get this value. For Z base is 132 squared divided by 100 MVA. So you get that value lah, 174, and so on. So you have to calculate the I base and Z base for each voltage level. Okay, in this manner lah. So once you know this one, you get the hang of it lah. You just know how to do for one voltage level. The other voltage level is the same. But what you have to be careful is the selection of the V base. Make sure it's the same lah to make your life easier when doing all this calculation. So source fault level, this is if it's given by TMB. For example, you are incorporating TMB, they give you, okay, their fault level there is 23 kA, for example. So 23 kA you convert to fault level, which is 23 times root 3 times, if it's at 132 times 132 kV, then you get MVA. So in this case, we use 100 MVA base. Let's say that TMB gives you 250 MVA fault level. So the source fault level is the S base divided by the 250 MVA by the source fault level. So 100 divided by 250. For transformer, it's Z% times S base divided by the S of the transformer. So in given here is 10% and 5 MVA. So it's 0.1 times 100 divided by 5 lah. 100 is the S base, 5 is the transformer MVA rating lah, or the base MVA rating of the transformer. Same goes for generator. Is the same manner, times S base and S generator. So if it's given you in kilowatt and power factor, so you need to convert them to MVA first. For motor, you have to convert them to MVA first, because normally they don't provide you in terms of mega MVA. So you have to know the kilowatt and the power factor. So you convert that kilowatt divided by the power factor and you get the MVA, then you will calculate the motor lah. Okay, and then for cable, so let's see that the cable here is 0.123 ohm per kilometer. So you know that the cable resistance is around 0.123 times 2 lah, about 0.246. So this is in terms of, still in terms of ohms. So to measure, to get the per unit of that cable, you just divide the Z cable by the Z base. So 0.123 times 2, which is the cable impedance or resistance, divided by the Z base, which is 1.21 ohm. So this one is taken from the previous slide as an example lah. So you will get the value lah. So I just purposely left all this blank for you to do calculation lah, with a calculator or by hand lah. Alright, so for motor generator transformer, you have to be careful with this one lah, because sometimes you may select that the system voltage is 11 kV as your base voltage, but your generator may be designed at 11.5 kV. So if that's the case, then you need this V old and V new in the formula lah. But if the V old and the V new base are the same, then it reduces to this lah. Alright. Okay, so that is an introduction to the per unit method. Okay. So let's go for the easier method, MVA method. MVA method only for balance fault and single phase to ground fault and estimation. But for balance fault, you can use this even for your exams. Those university students, if you forgot how to do the per unit method for balance fault, you can do MVA method, and I'm sure you will get exactly or almost the same answer unless your lecturer does not approve this MVA method to answer your exam. So the MVA method basically is a modification of the ohmic method, in which the impedance of a circuit is the sum of impedances of the various components of the circuits. And since by definition admittance is the reciprocal of the impedance, it follows that the reciprocal of the system admittance is the sum of the reciprocal of the admittance of the component, blah 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 blah. Let's forget about this and we go straight. We are practical and application engineer, so we go straight to the point. Okay, so let's how to do it. So as you can see, the name is MVA method. MVA is the apparent power. So we need to convert all the properties or the fault level into apparent power, MVA. So Y equals to 1 over Z. So this is admittance of a circuit. So KVA short circuit for a cable can be is using this one. For example, this is given, this is a cable. The impedance is 0.01 ohms and the voltage is 13.8 kV. So the MVA fault level for this is 1000 because it's kV. It's 0.01, so 0.01 is here lah. 1 over Z is here. So the voltage squared divided by the impedance. So you get the MVA lah. Alright. So another method is MVA divided by the Z per unit. This is for transformer. Okay. Okay, like in this case lah. So MVA short circuit is 13.8 squared divided by 0.01, which is V squared divided by 0.01, the impedance lah, V squared over Z. So 19,000 MVA. So this is the short circuit level of this cable lah. Okay. So we will go through later after this on how to convert the MVA rating of the transformer into MVA fault level for the source impedance, for the generator, for the motor. In the next few slides I will share with you lah. So once you've converted all those into MVA, the cable you've converted into MVA, generator you've converted into MVA fault level, the transformer into MVA fault level. So how do we sum up all this lah? So if the MVA, for example, should I draw a pen here? For example lah, so you have your MVA first here. Then you have your second MVA here. So if this is considered as series, then you have a lot. Okay, I'm just showing lah. For example, let's say this is a transformer, and this is your fault impedance from TMB. This is your internal generator, generator S3, S4. The fault level from the generators. So this is already converted to apparent power. So for the series side, we need to add up. How do we add up this one? This one we have to do it like a resistor in parallel. So this would come up to S1, S2 divided by S1 plus S2. So same. So let's name this as SX. So later when this value here is SX, so you have SX in parallel with S3 and S4. So for the parallel one, we just add up lah. SX plus S3 plus S4. So this is for the parallel one. So and this will become the equivalent MVA fault level when the fault is at this point. Let's say the fault is on this bus bar. So this is the final fault level. So once you got all this final fault level, you can quickly calculate the fault current here. So just divide by √3 times the voltage of this bus bar. Okay. Let's see here. This is one example. So here you have your generator 1500 MVA. It's already given like that. So that's the fault level given. So then you have your cable 69 kV and 3.87 ohms. And then you have your transformer 15 MVA 69/12 kV 0.076. This is already converted from percent. If it's in percentage, it would be 7.6%. Where else? Then you also have your motor 15 MVA with internal impedance of 0.2 lah. So your motor will act as a generator lah during the transient period of your short circuit. Let's say there's a fault here. Okay. So number one, what we have to do is you have to convert this to MVA. Step 1, convert to MVA. There's only 3 steps. Step 1, convert to MVA. So the fault level is given 1500 MVA. So for the cable, you need to convert is V squared over S over X. So V is 69 squared divided by the impedance, V squared over Z. So you get 1230. For transformer, it's just the transformer MVA divided by its impedance in terms of percentage. So 15 divided by Z percent, 0.076, and you get 198 MVA. And for the motor, since motor will also contribute to some short circuit level during the subtransient period, so similar like the transformer, it's just the MVA divided by the impedance. So 15 divided by 0.2 is 75. So this 75 can be reduced further. So actually, if you notice here, this 75, this line can be brought up here. So let me draw for you. Where is this pointer? Yeah. Okay. So let's say that this one is brought up here. We have 75. So for this one in series, you need to do it like a transformer in, like a resistor in parallel. So this one will be, let's say 1 over S will be equal to 1 over 1500 plus 1 over 1230 plus 1 over 198, and you will get this value lah. So then you will get S1. So when you get to the bottom one, you just add up S1 plus 75. So that will be the fault level at this point. So you divide by root 3 and 12 kV and you will get the short circuit current. Pretty much straightforward. So I think I may have gone too early in the previous slide. So once you've converted all the MVA, you must combine the MVA lah. Series MVA combines like a resistor in parallel. For parallel MVA, you just add it up lah. Okay, so these are the case. Then you will get MVA 1213. Okay, then 153 equals to 228. So this is the final MVA at this fault point lah. So 228. So 228, you just times 1000 divided by square root 3 times 12, which is the voltage of the bus bar. So you get 11 kA or 11,000 amps lah. Alright. So that is pretty much the steps lah. But sometimes it is hard to combine with a delta. So delta to Y connection lah. So this is, if you have interconnecting ring circuit or 3 substation, you want to add up between these 3 substations. So this kind of configuration is a little bit hard for you to do, whether it's parallel or not, or it's in series. So you cannot do calculation for this one. So you need to convert this connection from delta to star. So this is the formula lah. Okay. So let's say given Y1 equals to S over D1, so you have to calculate lah. Y1 equals to what? For example, 1 here, this is D1. This is D1. This is Y1, Y3, Y2. So just to show you lah what is meant here. So Y1 here is equals to S over D1. Y2 is equals to S over D2. So how you calculate S? This is the way lah. S equals to D1 times D2 plus D1 times D2 plus D2 times D3 plus D3 times D1. So this is if you ever encounter lah. When you draw and simplify the MVA, suddenly you find that there's a delta connection like this. So you must convert this to star connection like this, so that you can sum up easier lah. Alright. So third step is you reduce lah the MVA diagram. So reducing an MVA diagram takes the same reduction process required for the per unit impedance, except MVA quantities are used lah instead of per unit impedance. Okay, figure 7, figure 8. So we go through lah one by one. So this is figure 7 and figure 8. So figure 7, you have your initial your initial single line diagram. So number 1, you convert everything into fault level. So generator 20 MVA, maybe here is not showing you XD prime is 10%, 0.1. So 20 divided by 0.1, you get 200. And then this one is 13.8 kV squared, V squared over Z. So you get 100,000 MVA and so on. So here you can already see there's a delta connection. Once this one you sum up, so this one becomes a delta connection. Okay, so this one you sum up first, then you sum up this one, then it will become a delta connection. Alright, so this one you need to convert into star connection. Okay, so after you've converted everything, you need to reduce. So initially we had these two ni and these three here. So that 2 has been sum up and arrive to this value lah. Where else these 3 values 10, 5, 10, 24, you just sum it up, get 39. Okay, and then you change this delta into star, so you get this value lah, based on the formula that has been given in the past 3 slides or 2 slides. Okay, so once you've gotten to this point, you can sum up further. So this one will be in series, this one will be in series, and these two will be in parallel, and the result of this will be in series with 396. Okay, so you have to see lah, which point do you want to do the short circuit. So if you want to do the fault at this level, then you have to bring up everything with respect and sum up all the MVA with respect to this point of fault. So this is a lot more. Okay, 300. Okay, this one will be reduced further and further and further, and it's reduced much further lah, and so on. So we will not dwell too much lah, but that is the process lah. Once you understand the process of reducing the MVA, whether it's in series, whether it's in parallel, whether it's in delta connection, so you have to change to star. Then once you know how to reduce all this, then it'll make your life much easier. Okay, so MVA method, estimating voltage drop. This is also one of the advantage of using this MVA method. So large motors are frequently connected to the power system. So how do you want to calculate the voltage drop of a motor? So you can just calculate the voltage drop by measuring what is the short circuit level with respect to the motor, and using the MVA of the motor lah, MVAS, MVA short circuit. Let's see here. Example, you have your motor here. So this is, let's say, MVA S. Then you know that the fault level here is MVA short circuit. So what is the voltage drop? It's just MVA motor divided by the MVA motor plus the short circuit level at this point of fault. So this will be roughly an approximate value of the voltage drop estimation. Okay. So let's see in this case, so we have a motor here. Alright, so let's say the motor here, so this is a cable, transformer and the short circuit level of the bus. So this is for 500 MVA, it's 500 MVA, so cable no impedance, transformer 7.5 divided by 0.083, so you get 90 MVA, and also another cable impedance of the motor cable 1000. So let's say there's a fault here. So the fault here is how much? So the fault there is at F2 is 71 MVA lah. Okay, so for you to determine the voltage drop of this motor is 3.5 MVA. The starting motor MVA is around 21. So 3.5 is around about 6 times. So the voltage drop is motor MVA divided by the motor MVA plus MVA short circuit. So in this case, the motor MVA here is 21 plus 21, and 71 is the fault level at F2 here. So as you have calculated here lah, F2 71 MVA. Alright, so once you calculate that, you get the voltage drop is in terms of per unit 0.228, means it will drop around 22%. So the remaining voltage is about 80.5% lah. So if you think this material is good, please share this material to your electrical friends, and do subscribe to my YouTube channel, Crux of EE, and then my Facebook page. Please like my Facebook page, facebook.com/Crux of EE. And if you have any other questions, please throw them in the comments below, or you can email me directly lah at cruxofee@gmail.com. Thank you.